You don't need to be a weatherman to know which way the wind blows. Famous quote from Bob Dylan. And today's talk, for those of you who don't know me very well, let me just tell you that my undergraduate degree was in physics from the University of California at Berkeley. And my master's and PhD were from the University of Pennsylvania in Philadelphia, Ben Franklin's school. And I was trained basically as a nuclear physicist, but I've done a lot of other things in physics. And I thought it might be informative to explain to people just what the basic laws of chemistry and physics tell us about the Earth's climate and why it's changing. But before I do that, we need to understand the difference between climate and weather. Climate basically is the long-term behavior of our atmosphere, while weather is what happens every day. All of the short-term things that we see, rain, snow, wind, temperature changes, that's weather. But climate is what happens over the long haul. And by long term, we generally, in climate science, mean more than 30 years. And if we take a look at what's happened to our average global temperatures, basically since the start of the Industrial Revolution, they have been going up. Now, they don't always go up steadily. In fact, there was there was a period between about 1940 and 1980 when they didn't change a lot at all, this period in here. And I'll try to explain why that's so. But let me sum up in a sentence or two what physics learned in the 19th century. Basically, the 19th century was a golden era for both physics and chemistry. And Maxwell gave us understanding about electromagnetic radiation. The laws of thermodynamics were worked out pretty well. And it was pretty much understood that light itself was electromagnetic radiation. And about 1870 or so, physicists began asking a question of why the Earth wasn't colder than it was. They knew that a heated object emits radiation, and as the Earth turns and we go from day to night, we should have been cooling off a lot more at night than we did. The average temperature of the Earth, the whole planet, runs around 52 degrees Fahrenheit. And nighttime temperatures should have been getting pretty cold. If you looked at the Earth as a whole and looked at the energy coming in from the sun and the energy that was being lost at night because of radiation from the surface of the Earth should have had an average temperature not of 50, 52 degrees Fahrenheit, but more like freezing, 32 degrees. And they really didn't understand why that was what was happening until a few physicists in England did an experiment and showed experimentally that some of the minor components of the atmosphere, carbon dioxide and methane, were very good at scattering infrared radiation. They didn't quite understand why that was the case. It required the development of quantum mechanics to do that. But pretty soon they came to the conclusion that it was these minor components of the atmosphere that was providing something of a greenhouse effect. So one of the things we'll be talking about today is the atmospheric greenhouse effect and what it means for climate change. Okay, some chemistry. The cleanest burning carbon-based fuel is methane, natural gas. When natural gas burns, it makes a nice high temperature blue flame, and essentially complete combustion takes place. Natural gas is methane, and when it burns in oxygen, it produces heat, CO2, and water. The reaction is pretty simple. And it turns out that CO2 is a major greenhouse gas. It's one of these gases that scatters infrared radiation. Now, we're going to see that the presence of greenhouse gases in the atmosphere is basically the reason why nighttime temperatures on the Earth are not drastically colder than daytime temperatures. Now, when other fossil fuels are burned, things like coal and oil, the carbon compounds in these fuels also produce a large amount of CO2, along with some methane, which is also a greenhouse gas. But coal and oil also contain nitrogen and sulfur-based compounds. And when they burn, they produce oxides of nitrogen and sulfur that end up in the atmosphere as well. And they can have an effect on how our global temperatures behave. Let's talk about the atmospheric greenhouse effect in detail. The Earth receives on average about 340 watts per square meter of incoming energy from the sun. Most of the incoming solar radiation is in the visible and ultraviolet. We know that because if you look at the sun, it's very bright and white. And those are short wavelengths. This incoming solar radiation warms up the surface of the planet, and the warm surface radiates back out towards space, but the outgoing radiation is almost all in the infrared wavelengths, the long wavelengths. Does anyone know why that's the case? We've got a couple of physicists online here, and you go back to Planck's law, and it tells you where the peak in the spectrum from a hot object, the electromagnetic spectrum from a hot object is. And the sun's a very high temperature surface, but the surface of the Earth is not high. So at night, on the night side of the planet, the infrared wavelengths dominate. And without the greenhouse effect, they would just radiate out into outer space at night. The average temperature of the Earth would drop to about 32 degrees Fahrenheit, though it would be much warmer than this during the day and much colder than this at night. And it's basically these minor components of the atmosphere: water vapor, carbon dioxide, methane, nitrous oxide, that absorb the infrared radiation and scatter it essentially, while the major gaseous components such as nitrogen and oxygen, which make up pretty much most of the atmosphere, are transparent. The infrared radiation just goes right through them. Now, let me just mention, for those of you who are not physicists, that light has both wave-like and particle-like properties. We've all seen how a prism can break up a beam of incoming white light into a spectrum of colors, which, with the red light having the longer wavelengths and blue light having the shorter wavelengths. But in the laboratory, we can do experiments with weaker and weaker and weaker light beams until eventually we can deal with individual particles of light, so-called photons. And today I'll be switching back and forth between the descriptions of the incoming radiation, the white light from the sun, and the outgoing electromagnetic radiation from the surface of the Earth. Sometimes I'll talk about wavelengths. Sometimes I'll just talk about photons, the number of particles of light coming in and going out. So hopefully that won't confuse you. It wasn't really until the early part of the 20th century that we understood the atmospheric greenhouse effect. It took quantum mechanics, which basically revolutionized chemistry, for us to fully understand what was going on. Now, even though the carbon dioxide and methane molecules in the atmosphere comprise only a really small fraction of the atmosphere, they are very, very effective at absorbing infrared radiation. Now, let me also mention that between in addition to carbon dioxide and methane, there are other naturally occurring, there are other greenhouse gases that aren't naturally occurring, but are actually man-made. These include the refrigerants such as Freon, but if those get in the atmosphere, they also contribute. Now, when a carbon dioxide atom absorbs an infrared photon, quantum mechanics tells us that its energy increases a tiny bit. The atom starts vibrating a bit. You get these vibrational and rotational levels. A short time later, really short, much less than a microsecond, the excited carbon dioxide atom will kick an infrared photon out. But the thing that makes for the greenhouse effect is the fact that the direction in which the photon is then emitted is random. And there's about as high a chance that the emitted photon from an excited carbon dioxide molecule will be emitted towards the Earth's surface as towards outer space. And it's this fraction of the re-radiated infrared energy that's directed back towards the Earth that essentially produces the atmospheric greenhouse effect. Now, the atmospheric greenhouse effect is not the same as what happens in a real greenhouse, a true greenhouse, but it's similar. It's like having a sort of a blanket in the atmosphere that keeps us from really getting down to very, very, very cold temperatures at night. This picture shows a snapshot of the Earth's solar energy budget at a particular time. And I'll explain why this refers to just a particular time. If we think about the incoming solar radiation during the day, let's suppose that this is either 100% of the incoming solar radiation, or let's just say it's 100 photons coming in. Then what happens to these 100 photons that hit the atmosphere from the sun? Well, a certain number are absorbed by water vapor, dust, and ozone in the atmosphere. A certain fraction is absorbed in clouds. Some of it gets scattered back out by the air itself. Some is reflected from the clouds, and some ends up reflected from the surface, particularly areas where there's ice and snow. That's going to reflect solar radiation fairly well. And at the time this chart was made, basically for every 100 photons that came in from the sun, about 51 of those 100, or 51% of the light coming in, essentially was absorbed by the surface of the Earth, 70% covered by ocean and the rest by land. Now, at night, this infrared radiation re-radiates out into space. But not all of the heat that comes off the Earth during the nighttime hours is due to infrared radiation. There's a certain amount of what physicists call sensible heat flux, and that's just convection from the surface. Just if you're close to a fireplace, you can feel the radiant heat, but if you're outdoors near a fire, you often feel a warm air flowing by, and that's what we mean by sensible heat flux. And a certain portion of the thermal energy on the surface of the Earth at night leaves by basically water vapor evaporating, and that's what we call the latent heat flux. So of the 51 photons that hit the Earth, 21 end up being emitted as infrared radiation from the surface, and about 7 is sensible heat flux, and 23% comes off as latent heat flux. It's really these two numbers here, the 21 photons, infrared photons that get radiated out at night, and the 6 of them that make it through the atmosphere without being absorbed, and the 15 that get absorbed by the greenhouse gases, water vapor, CO2, methane, and so forth. What happens is that of these 15, because of the re-radiation from these greenhouse gases, about half of those go back towards the surface of the earth. And that's essentially where the atmospheric greenhouse effect comes from. It's from these 15 photons that get scattered in every direction. Now, in a real greenhouse, you don't have heat loss by as much by these methods. If you've ever been inside a real greenhouse, you know there's no evaporation. It's very, very humid. And this is the reason why a real greenhouse is much more effective at trapping energy than the atmospheric greenhouse. But the atmospheric greenhouse effect is important because it makes the planet have a climate that's much more temperate. We don't have really huge variations in temperature between day and night. And basically, all of life on Earth has evolved in this kind of environment. Now, as I said, this picture is a snapshot. And what's happening in climate change is that if these greenhouse gases like CO2 start increasing in amount, then more nighttime radiation is going to be reflected back towards this, is going to be scattered back towards the surface of the Earth. And slowly the Earth is going to warm up. And basically, physics is telling us that there's no way out. You can't argue your way out of the atmospheric greenhouse effect and the contribution that CO2 makes to that. Now, this is just talking about the numbers, but the bottom line is down here in the last statement. That basically, this is where the greenhouse effect comes from. And as long as you're burning fossil fuels, which give us carbon dioxide, methane, and other greenhouse gases into the atmosphere, the Earth is going to warm up if the amount of those changes markedly. Now, prior to the start of the Industrial Revolution, the carbon dioxide content of the atmosphere came solely from natural sources. It involved exchange from the oceans, volcanic activity, and respiration of animals. The natural sources of carbon dioxide were largely balanced by natural sinks, such as direct absorption by the oceans and photosynthesis. You know, all of agriculture depends on photosynthesis, and carbon dioxide is very important from that. Now, if we look at how the carbon dioxide content of the atmosphere varied in the past, we find out that prior to the Industrial Revolution, the carbon dioxide content of the atmosphere was pretty stable. It varied in a narrow band between about 200 parts per million and 300 parts per million. How do we know that? Well, some really nice work was done in looking at ice cores from the Antarctic. These ice cores, when they were pulled out of the Antarctic, basically gives you a record in time of the carbon dioxide content, because there are little bubbles of gas in the ice cores, and you can examine the chemical content of those bubbles, and you can determine how much carbon dioxide was in the atmosphere. And we have data now going back almost 800,000 years prior to the Industrial Revolution that we can look at. And here's some of that data. The reason I've got this slide up is it also shows the methane content in the atmosphere as well as the carbon dioxide. And this only goes back 400,000 years before 1950, but you can see that the carbon dioxide was varying between about 300 parts per million and 200 parts per million for all this time. This is a long time, and we're talking 400,000 years. Now, there's much less methane in the atmosphere, and that also varied within quite narrow limits over the same period of time. It was between 400 and about 650 parts per billion. Now, this slide shows the CO2 going all the way back to 800,000 years before the present. And as you can see, there were these warm-ups and cool-downs, warm-ups and cool-downs. And over the entire period up to about the beginning of the industrial age, never got above 300 parts per million, never got much below 200 parts per million. The other thing about this, these data that's interesting is that the rise in carbon dioxide, if you look at one of these curves, is actually over a very long period of time, literally thousands of years. In fact, the warming started before the carbon dioxide content of the atmosphere began to increase. There are small variations in the orbit of the Earth around the sun over the millennia that cause additional heating and cooling, small amounts, but it was enough to get more carbon dioxide into the atmosphere. And then when things cooled off, the carbon dioxide content would come back down. But the important thing is these time scales are much, much larger than what happened when the Industrial Revolution began and we began to burn a lot of fossil fuel. Now, this gives you an idea. At the very end here, we can see what the 2018 carbon dioxide content of the atmosphere was. It was over 400 parts per million. And look how fast it rose. Because now the increase in carbon dioxide was not being caused by natural processes, but it was being caused by something that human beings did. And people looked at this, and poor old Al Gore got a lot of flack about the hockey stick graph. This is the hockey stick right here. People argue that this couldn't possibly be right, that this wasn't real. And it turns out that Al Gore was right all along. Basically, what we have done by burning large amounts of fossil fuel is we have put much more carbon dioxide and other greenhouse gases into the atmosphere than were in them prior to the industrial age. Now, one of the things you really need to remember is that virtually all life on Earth developed with a climate where the carbon dioxide content varied between about 200 parts per billion per million and 300 parts per million. Keep that in mind. We human beings, all of the animals on the Earth, all the sea life, all of the all of the plants that grow on the Earth, they all developed with this kind of a background in greenhouse gases. What's going to happen when we move into an era when the amount of carbon dioxide and other greenhouse gases is much higher than we had over the period in which evolution took place. Well, what is really happening to carbon dioxide? We have very good data on that. Scripps now, the Scripps has had a carbon dioxide measuring program on Mount Mauna Loa in Hawaii for a long time. And if we take a look, we see that starting about 1955, where this chart begins, where they first started measuring, that there has been a steady increase in the amount of carbon dioxide in the atmosphere. You see this oscillation, that's just an annual cycle. But if you look at the trend, it's been steadily upward with very few changes since about 1955 to the very present. And right now we're up close to around 420 parts per million of CO2 in the atmosphere. And this is much, much higher than it was. You know, it's basically a third higher than it was for most of history of the Earth. Now, what we can say is that in the absence of other factors, the increasing CO2 in the atmosphere will cause the Earth's surface to warm. That's just basic physics. There's no way around that. Are there any influences that can counteract the effects of increasing greenhouse gases? And the answer to that is yes, there are. For example, we know that volcanic activity emits some CO2 into the atmosphere, but it also can eject large amounts of very fine particulates into the upper atmosphere. This happens particularly when there's not just volcanic activity, but explosive volcanic activity that raises the fine particulates very high in the atmosphere. For example, in the late 1800s, there was a volcanic explosion on Krakatoa in the South Pacific that put a huge amount of fine particulates into the upper atmosphere. Now, these fine particles can reflect some of the incoming solar radiation, and that in turn can cause the surface of the Earth to cool. For about a year and a half to 2 years after Krakatoa blew its top, there virtually wasn't any summer worldwide. It was winter for almost a full year. But typically the fine particles don't get emitted that high, and typically they don't remain in the atmosphere for long periods of time. So their influence on average surface temperatures seldom is longer than a year or so. And let me see if I can get back to that. Talking about the fine particulates, they're predominantly sulfur dioxide particles. Now, another source of sulfur dioxide particles in the atmosphere is the combustion of fossil fuels that contain high levels of sulfur. Basically, not natural gas, but coal and oil. A lot of coal and oil, when you burn it, produces sulfates as well as carbon dioxide and methane. And from about 1940 to 1980, significant amounts of sulfate particles enter this lower atmosphere from coal-fired power plants and from burning oil. The scattering of incoming solar radiation from these particulates counteracted much of the increasing greenhouse effect from increasing CO2 emissions. But for us old timers, we remember that the sulfur compounds that were ejected into the atmosphere were a major source of something called acid rain and smog. So that eventually pollution controls were instituted in the major industrial countries around the world to reduce these emissions. And this largely eliminated this anti-greenhouse effect by 1980. And let's go back to another slide here. This actually is a slide that came from the Japan Meteorological Agency. And they have a very nice presentation, I think, of global average temperature anomalies. And these were for the month of May, going back to about 1890 when they started taking data. And you can see, if you follow the blue line, which is kind of a 5-year average of what's happening to the temperature of in the atmosphere, you see that from about, roughly 1950 or so to about 1980, things were pretty flat. That the particulates in the upper atmosphere caused by sulfates were pretty much balancing out the increasing carbon dioxide that was happening during the same period. But things got so bad with acid rain and smog that around the world, pollution controls started to be put into effect. Stationary coal burning power plants could have scrubbers added to them that took most of these particulates out. Smog controls were added to automobiles. And even though from about 1945 on, there was a huge increase worldwide in the consumption of electricity that caused this sort of flattening of the curve until about 1975. Once the pollution controls went into effect to eliminate acid rain and smog, then the carbon dioxide increases started to win again, and we can see that that the global temperatures have been increasing ever since then. Now, at this point, let me ask you if you have any questions. Anybody out there want to ask a question about what's happening?
I don't quite understand what's happening. What I want to know is what can we do to prevent this happening?
Well,
are you going to get to that?
Yes, we will get to that. Basically, we know what's happening. The carbon dioxide is increasing along with other greenhouse gases, and as long as those increase and we don't have any countervailing effects, the global temperatures and all that entails are going to continue to rise. So the basic answer is you have to stop putting so much carbon into the atmosphere. I mean, that's basically the answer. But let me talk a little bit now about climate.
Mark?
Yes, go ahead.
This is John Olmsted.
Yes, John.
There's a temperature spike in 1998 on that Japan graph, and I'm wondering if there's any global meteorological event that accounted for that.
You're talking about the previous slide?
Yeah, but the Japan, see, 1998, it's well above anything, and so something must have happened.
I'm trying to remember. I think that was a really bad El Nino year or something like that.
Yeah, Mark, a lot of those wiggles and spikes in the annual record are associated with what you just said, El Nino or La Nina.
Yeah.
Those affect global weather and temperature quite a bit.
Yeah, and I think that big spike probably was a major El Nino event, but exactly. I'd have to go look at
That's
that.
Right.
Thank you.
Like I say, weather varies a lot. Climate changes more slowly. So you really have to look at a 30-year period. And basically, like if you go back to this flat period, you find that it's about 30 years long. So if you limit yourself when you talk about climate to what happens over a 30-year period, you typically catch most of what's happening to the climate. But as long as we continue to burn fossil fuels and put greenhouse gases into the air, these curves are going to continue to go up. They vary from year to year, but they keep, on average, they keep going up. And there's, the only way you can stop that is to really stop the amount of carbon that you're putting into the atmosphere. Okay, I haven't talked.
Could I ask a question? I'm Conrader. Can you
Sure, go
bury, can you bury CO2 in the earth in large quantities?
That is one of the suggestions. I believe Iceland is trying to do that. I'm not sure how well that would work. Another suggestion people have made, which I think is a very dangerous suggestion, is to artificially put more fine particles into the atmosphere to basically change the reflectivity of the Earth. And, that's an experiment with the atmosphere that I think would be very dangerous. Taking carbon dioxide out and sequestering it may be a possibility. It's not clear how much energy that would require. And if it requires a huge amount of energy, the net gain may not be that great.
The sequestering occurs every day with the growth of plant life and.
Yeah, but that's a cyclical process.
Right. Oh, okay.
So,
Increase
Mark, it'll be hard for you to keep moving along with your talk.
Yeah.
With all of our questions.
Yeah, we'll save some.
I do have some explanation for the 1998 spike and what's been going on. When that comes up, if you'd like.
Sure. Thanks, Steve. Let's continue on here. Let's talk about climate models. And why do we need climate models? Well, what we've learned from physics and chemistry applies to the Earth as a whole, but it doesn't really tell us much about what's happening, from place to place. It doesn't tell us the details of how the increase in the global greenhouse effect interacts with weather. And you need climate models to do that. The dynamics of the climate system are fairly complicated, but there are at least 7 physical principles that are involved in the climate models. Conservation of the air mass, the amount of air that we have doesn't change. Conservation of water mass, and again, the water in the atmosphere doesn't really change that much. And the reason for that is that the water cycle is so short. If you eject a water molecule into the atmosphere, it only stays in the atmosphere for around 30 days. Conservation of energy is a basic physical principle. You have to conserve energy, balancing what comes in from the sun and what leaves. And you have to conserve momentum in 3 directions for the atmosphere. And the ideal gas law also has to apply. So that amounts to basically 7 equations, because you've got 1, 2, 3, 4, 5, 6, 7 if the 3 directions. And these are things that you can compute from the laws of physics. But there are they constrain several things about the atmosphere. They constrain the air temperature, the pressure, the density, the water vapor content, the wind magnitude. And if you solve these equations, the climate model should be able to simulate all these variables in 3 dimensions and in time. But there's a lot of things that they don't take into account. For example, they don't take into account the effect of clouds. They don't take into effect things like rain, snow, and evaporation in a very good way. You have to essentially parameterize those in the climate model. So what is parameterization? It means your best guess, really, as to how they're going to affect things. And there have been a lot of climate models that people have come up with to try to predict how global warming is going to affect us, not just on a global basis, but on a local basis. And there are probably 20 or 30 decent climate models. For a climate model to be relatively good, it has to do at least one thing very well. It has to predict past behavior. In other words, if you run your model on the computer in, say, 2000 or 2005, and then you look backwards, what did your model say about the climate before 2000 or 2005? Because we know what the climate did then. And the answer is that the models actually have been improved to the point where they're quite good at predicting the future behavior of the climate as well as the past behavior of the climate. And we'll show that on the next slide. Okay, this is a combination of what happened for about 20 climate models that were run in 2004, 20 different climate models. And the red line tells us what the atmosphere did from about 1970 to about 2020. And the black line is the average of the predictions from these different climate models. And you see that if you look at the average, it's not too bad. You know, the average of all the climate models gets you to pretty much what the climate did. That's encouraging, that telling you that the models aren't that bad. But if you look at the light blue, you see that there's a pretty big spread from one climate model to another. But there's one thing that's true about all the climate models. The ones that predict the worst case and one that predicts the best case, it doesn't matter whether you're looking at the model with the best case or the worst case, they're all going up. They're predicting that the temperatures are going to continue to rise. Some models predicted that they'd rise more slowly. Some would predict they would rise more rapidly. And the reason for that was pretty easy to understand. Some of the models did not account properly for the amount of heat and CO2 that was being absorbed by the oceans. Now, the surface of the Earth is, 70% water. So a lot of what happens in the oceans, as Steve Murray will be very happy to tell you about. Now, the ones that did not account properly for the amount of heat and CO2 that was being absorbed by the oceans, these tended to predict global average surface temperature trends that were too high. On the other hand, the models that overestimated the reflection effects from fine particle emissions, they predicted temperature trends that rose too slowly. The basic conclusion from both the models and from the laws of chemistry and physics, however, is that so long as the levels of greenhouse gases continue to increase, global temperatures will rise. There's really nothing you can do about that except stop putting so much greenhouse gas into the atmosphere. Now, let's talk a little bit about what's going to happen to us because of continued rising temperatures. We're going to see more extreme weather events, more heat waves, more drought in some areas, floods in others. We'll see rising sea levels because as the atmosphere warms, more ice and snow over the continents melts. And that melting water gets into the oceans and the sea levels tend to rise. As the atmosphere warms up, melting of glaciers will take place. And I don't think a lot of people realize it, but there are many parts of the world where the drinking water supply comes from glacial meltwater. So there's going to be problems with enough clean drinking water in several parts of the world. The other thing that we don't have time to talk about in much detail, but is very, very important, is ocean acidification. As the ocean acidifies because of the fact that it absorbs more carbon dioxide, which produces more carbonic acid, that's going to have a significant effect on the food chain that we depend on from the ocean. Again, all of sea life, both the animal life and and the plant life within the sea evolved with carbon dioxide levels that varied between about 200 parts per million and 300 parts per million. We'll also see more intense storms. And the reason for this is the fact that as the ocean warms, the storms, which mostly form over the ocean, pick up more energy from the ocean. The temperature of the ocean really determines what storms look like. Eventually, we'll see an ice-free Arctic because the Arctic actually has been warming faster than any other part of the Earth for a reason I'll discuss in a little bit. We'll also see longer growing seasons. For people who don't believe that climate change is happening, all you have to do is ask a farmer or someone who grazes cattle, and they will tell you that the growing seasons are now longer and they can graze cattle at higher altitudes than they ever have before. But in addition to the longer growing seasons, we're also going to see much longer wildfire seasons. And we know that, that in many parts of the world now, the wildfire season is not just a fall event, but it's a year-long event. And we'll also see an increasing number of heat-related illnesses and deaths. That's not talked about very much, but there are parts of the world now that get so hot that they're almost unlivable unless you have air conditioning. So these are all of the, not all, but a lot of the important effects that we're going to see because of continuing rising temperatures unless we do something about it. These are all the predictions of the models and the predictions of the physics and chemistry. What does the data tell us? Okay, what about extreme weather events? And one good way to measure extreme weather events is just simply to count the number of new record high temperatures that are measured around the world and the number of new record low temperatures. We continue to see, snow in winter. We continue to have days when the temperatures are very low. But if you look and just count around the surface of the Earth from, all the weather stations that we have and add up the number of new record high temperatures in a given year and compare them to the number of new record low temperatures in the same year. In recent years, the number of record high temperatures has substantially exceeded the number of new record low temperatures. What about sea level rise? This is something that people have measured well over much more than the past century. And the data is pretty clear that, say, between 1995 and 2022, that the mean sea level around the world has increased 20, 40, 60, 80 millimeters. That's 8 centimeters. That's 8 centimeters is about a third of a foot. In a relatively short time, in about 30 years, the sea level has increased about a third of a foot. Over a century, that means you're going to increase sea level by a foot. Now, that might not sound like a lot, but that's the mean sea level around the world. There are lots of parts of the world where the average elevation is not a whole lot more than a foot above sea level. You have countries like Bangladesh that are essentially going to end up being underwater, as well as a good part of Oceania, a lot of the islands in the Pacific. I mean, they're already seeing sea level rise that's causing them to have to abandon certain atolls that people live on. So, you know, that's something that continues to happen. If you go to areas like Florida, they see flooding on a regular basis. Here in Southern California, we get king tides, and we regularly now get flooding of residential areas because of the fact that the mean sea level has risen. Retreating glaciers. These are some data about the average reduction in ice mass in glaciers around the world. And we can see that between 45, they've been measuring this since about 1945. And we can see that over the past 50 years or so, there's been about a 23% decline in the amount of water that's present in glaciers. That's going to have a tremendous effect on the water supply for a lot of people around the earth. And also, this is adding to sea level rise. This is this is the reason why the sea levels are increasing.
Mark, I want to
Yes.
say one thing, that the biggest glacier is in the Himalayas, and which is filling Indus, Ganges, Brahmaputra, and from the China side, 2 more big rivers. So almost 5 big rivers. And the Himalayan glacier has reduced substantially, I heard. Do you have any comments on?
I don't have any knowledge of the specific glaciers, except for except for some of the glaciers that we have that I personally have walked on. We took several cruises to Alaska when we first started cruising after I retired fully in 2007, and one of the places we would often go to would be the Mendenhall Glacier in Alaska. And, you know, that was a short ride from the ship to the Mendenhall Glacier. Now it's a long ride from the ship to the Mendenhall Glacier. So they are definitely, the glaciers are almost all in retreat. Not every one of them, but almost all of them around the world are in retreat. And this does have a substantial effect on the water supply.
In your geological history, do you have any parallels to this? Did it happen before?
Not that I'm aware of. Not that I'm aware of. You know, written history doesn't go back that far. But
It's scary.
Yeah, I mean, the data go back 800,000 years. There weren't people walking around on the earth then. As far as the intensity of storms is concerned, we see this a lot. And these charts here show you basically the number of intense storms, the frequency of storms and the intensity of storms in the high latitudes and in the mid latitudes. And you can see that as time has gone on, the intensity of weather events has just grown, particularly in the high and mid latitudes. And this is causing major problems. For example, flooding is becoming much more frequent in areas because of these storms. We've seen this particularly in the Northern Hemisphere, just a lot of very extreme weather events that just didn't used to happen like that. And then what's happening in the Arctic is really interesting, because that's the part of the globe that's warming the most rapidly. Climate change doesn't affect the surface of the earth uniformly. It varies from place to place because of the interaction with the weather, and also because of some feedback effects that are unique to the Arctic. But if we look at the sea ice coverage in the Arctic over the course of a year, and look back about 20 years when we really, 20 to 40 years when we really started measuring this in great detail. This is the average here. We see that, of course, sea ice declines from winter to summer. But if you ask what's happening in recent years, on average, it's significantly lower than it was when we first started measuring. And this explains why the Arctic is warming so much faster than the rest of the planet. It's what we in physics call a positive feedback effect. When you lose sea ice, oops, let me go back a little bit. When you lose sea ice, you're changing the albedo of the surface of the Earth in the area where you're losing the sea ice. Also, when you lose snow, you're changing the albedo of the Earth. The albedo is just a fancy word for the reflectivity of the surface. And ice and snow reflect sunlight much more efficiently than just the ground and ocean water. Ocean water looks black when you take the ice away. And that means that the ocean warms up faster. If you take snow away, that means that the land surface warms up faster. And if it warms up faster, that melts more sea ice and that melts more snow. So that's a positive feedback effect. And basically, we're seeing a much, much more rapid warming of the Arctic than any other part of the planet. But it's understandable from just the basic physics of what's going on. Now, what about heat-induced illnesses and deaths? This is something that people don't talk about very much, but when you increase the average temperature 20 to when you increase the average temperature in various parts of the world, that increases the amount of mortality that can be attributed to heat-related illnesses. And if you look particularly in the sort of the equatorial countries, you can see that, hey, this is really getting bad, that the relative number of deaths from heat-related illnesses has increased, something like 50% in recent years. It's not as pronounced in other parts of the world, but if you get to like Kuwait and Iran, which is very warm climate, yeah, that's getting pretty bad. And the Philippines, Thailand, and Vietnam, that's also getting pretty bad. So basically, there's a lot of human illness and increased death that's happening because we have climate change. It's not talked about much, but people are starting to recognize that this is really a significant factor, and that there are really parts of the world where it's getting almost impossible to live without putting yourself at risk. And that's decreasing longevity and so forth. Now, I did talk about the feedback effects in the Arctic, and our hour is just about up. So now's a good time to ask questions.
There's going to be there's going to be a survey, a meeting in Ireland or Scotland coming up. Do you think they will make any significant contributions to what's happening or what will be done?
I don't know. I really don't know. Hopefully, people are starting to recognize that climate change, number one, it's real, it's really happening. This is not some political question. It's a real physical, physics and chemistry is driving this. And the only way we get out of it is to stop putting so much greenhouse gases into the air. But it remains to be seen what the politicians will do. There are a lot of economic pressures against climate change controls, but I always ask people, yes, it's going to be costly to combat climate change, but you have to measure the cost of combating climate change against the cost of not doing that. And the costs of not doing that now are starting to become obvious and significant. Other questions? Steve, did you have something you wanted to say about some of the weather data?
Sure. So John Olmsted asked that question about 1998 and the spike. And I have two things to contribute to that. First of all, that was indeed a period of a very extreme El Nino event. Now, El Nino events, I think most